So now let's move on to our second topic, which is vectors. A vector is a quantity defined by a magnitude and a direction. So you can't really get a vector confused with coordinates because they're quite different. A coordinate is a place. A vector doesn't care where it is, it just cares the direction and magnitude that it moves in that direction. So we like to represent vectors with arrows, where the length would represent the magnitude and the direction would be represented by the way that the arrow faces. So let's say if it's on a plane, the direction we could think of as like maybe the angle from the x-axis, which is a very common way to consider the direction of a two-dimensional vector. Now, two vectors, that means two vectors are equal, not based on their initial position. They don't have an initial position that actually defines them. You could place them from somewhere if you wanted to, like with some geometric questions, you put them somewhere, but we would consider them equal to another vector if their directions and magnitudes are equal. That means, let's say I have a shape that has positional points. Let's say I have this shape here. I have A, B, C, D. The vector that we can say is from A to B, and we write it like this, is the same as the vector from C to D. I'm sort of assuming with this shape, this sort of rhombus, I guess, that C to D is the same length, and that they are parallel to C to D is the same length as A to B, and C to D is parallel to A to B. If that's the case, these two vectors are the same vector. They are equal because they have the same direction, they have the same magnitude. So we like to write a vector from between 2 points. Let's say it's from A to B as such, like this, A to B. We can also just give a vector a value like this, though. We can just say A to B equals A. We can just give it a variable like anything else. Now, the magnitude of AB, we would usually write this. We use two vertical bars, and we put it outside of the vector. So we could do it like this as well if the vector is A. Now, a unit vector is any vector with a magnitude of 1. These are useful for some specific types of questions and problems that we like to solve. So let's look at the multiple forms of which we can write vectors in. So we have something called column form or matrix form. Basically, for this and component form, we split up what a vector is into components, into parts. So for column notation, instead of writing a direction and magnitude, we describe it, if it's a 2D vector, we can describe it with two magnitudes. So we can describe a vector with two magnitudes if it's a two-dimensional vector, let's say A and B. And for example, we could say 3, 1. Then if we were to plot this on like a plane from the origin, we would say probably looks something like this, because it moves to the position 3. It points towards the position 3, 1 on this plane. Component form is quite similar to this, except we separate it into these components. We write it like this. So this is a two-dimensional vector as well. We have 3i plus 1j. J is basically the direction along the component. J is the component which moves along the y-axis, whereas I is the component which moves along the x-axis, if you were to represent these on, say, a Cartesian plane. Now, polar form represents a vector more so as what it is. It represents a direction and a magnitude. So that would be magnitude first and then direction. The direction, if we're thinking in terms of like a Cartesian plane, we would usually represent the direction as being an angle anti-clockwise around the from the x-axis, sorry. So sort of moving like this, and then whatever angle that is the angle of our vector. And the magnitude is obviously, again, the length. So in this scenario, the magnitude of this would be 3 squared plus 1 squared, and then the square root of that, because we could draw it as sort of a triangle and use Pythagoras' theorem to find out what is the actual length here, what is the magnitude of that. So let's actually do a question where we convert between forms of interpreting this vector. because that can allow us to get an understanding of what is polar form relative to component form. And this is useful because some problem solving questions, it might be useful to interpret a vector in a different way. So to convert A, which equals to 12i plus 4j into polar form, we want to consider its magnitude and its angle. We can use Pythagoras' theorem to find its magnitude. So, for example, this is a pretty simple. Do remember to, if you're drawing a triangle, let's say this was negative, do remember that you should draw it like this to not confuse yourself, because we're thinking in terms of we're on some sort of set of axes, and if the I component is negative, we need to move backwards along the x-axis. But for now, we just have 12i plus 4j. So I can put a 12 down there and a 4 there. And then we have the angle in here. And then we have the magnitude up here. So the magnitude, based on Pythagoras' theorem, will be the square root of 4 squared plus 12 squared. And the angle will equal the inverse tan of 4 divided by 12, because that is opposite over adjacent of the angle. So I can quickly use my calculator to find that m is 12.65 based on this, and that the angle is 18.44. So then our polar form can be written as 12.65 and then 18.44. And of course, we can't remember our type of angle we're using, because often we might use radii. So radians, sorry. Now let's consider some simple operations on vectors. So we have addition first. Now we should note that addition is commutative. That means b plus a is equal to a plus b. That doesn't matter what order you put them in. If it's just addition, it's the same. We can prove that by looking at arrow representations of vectors. So even if over here we have a goes first and then b goes first, and then you can see the final line that it generates, which is a plus b. Instead, we can put b first and then a, but then this final line looks the same. So we have a commutative sort of operation here. Now, vector subtraction is sort of a little more interesting to look at. If we subtract b from a, we get the vector that goes from where b ends up to a, if they started at the same location, if you place them sort of geometrically like that. So that means it isn't commutative. A minus b does not equal to b minus a, because let's instead do this line as b minus a. We have a and b. Now b minus a goes in the opposite direction. So it might have the same magnitude, but it doesn't have the same direction. It actually has the direct opposite direction. So they are not commutative in terms of subtraction. Now, scalar multiplication is pretty simple. When you multiply a vector by just a simple magnitude value, all you do is you multiply its magnitude by that value. Direction doesn't change at all. So if I said, if I have this line, and then I multiply this line by 2, you could just imagine it gets 2 times as long. And that's what scalar multiplication is. So if I have k times a, and a is a vector, then the magnitude of that will be the magnitude of a times k. Of course, as well, you can multiply vectors by a negative scalar, and then they will go in the opposite direction. So that is actually the one instance where direction does change. I should be clear about that. You can multiply them by a negative number, and then it will go in an opposite direction, but you can't change the direction other than flipping it. So let's look at actually doing some addition using component form, which I would say most operations that you're going to be working with, component form, or you could also put it in, column form, matrix form. These are the easiest forms to operate in. So A is equal to 10i plus 5j. We could try to represent this as sort of like this line here, where we have 10 across and 5 up. And then we have B is 5i minus 10j. So we could represent this as sort of a line going down here, where it goes 5i across and then 10j down. So A plus B is equal to simply all of the components added together. So we can make this very easy on ourselves if we're using component form. Polar form would be a lot more difficult to recognize, like how to find a solution. So that's 15i minus 5j, and that's our answer. Now let's do this for this question down here, but let's use matrix form instead. So if I was to represent A in matrix or column form, I would say 12 and then 4. And then we have, so that's A equals, and then we have B equals 6 minus 3. So if I want to subtract B from A, that would be the vector that goes between that goes from B to A. So we can simply do it like this. We have 12, 4, minus 6, 3. And then we can, of course, use our normal understanding of maths to interpret it as we can flip it to a plus, and then we can flip all the signs inside these brackets here. So then the resulting matrix vector would be 6, 7. And that would be, this is the line that goes from B to A. This is the vector, sorry. So what is the vector from A to B? To do that, we should do B minus A. So 15i minus, 4i minus 15i. Then we have minus 9j minus 4j. This all equals to minus 11i minus 13j. And that's our answer. So we can also have vectors with more dimensions. The highest we often actually work with, because we're often thinking of our physical reality we live in, is we work with vectors in 3D. Now, all the same forms can apply, they're just a little bit extended each time. So for matrix form, we just have one more value down here. So we have A, B, C now. So we have a C instead of just two values that we were utilizing at this point here. And then we can like addition, subtraction, scalar, multiplication works pretty similar. You just do it on all components as opposed to two. On three components as opposed to two, sorry. Then in terms of component form, we use I plus J, and now we just add another one. We use K. Then in terms of polar form, we can just add one more angle, and then we have a solution. So if we were just on the x and y axis, let's say we had a line going down here, it might look sort of like this, and then there's our magnitude, and then there's our angle. But instead, we actually have a line going up here now into like 3D space. So then, if this sort of goes up to there, if this line in 3D space is directly above that line, all we have to do is we have to add this angle in here, and that will probably use a different symbol. If we should add an angle in here, and that will, let's use this symbol. We'll add an angle in here, and that will work with everything. So that means we have M, this symbol, and this symbol, and they represent angle 1 and angle 2. So this is the angle clockwise from the x-axis, from the direction of the x-axis, and this would be the angle from the direction of the z-axis. So we're going to work with addition and subtraction with these 3D vectors. Now this is 3i plus 1j, so that's our normal 2D. This is 5j minus 1k, so that is like in our 3D space now, because we're moving up the z-axis with that k involved as well. Then we have c is a minus b, d is 3i, so that's a full 3D vector with all three components. So what is the vector from D to C? So first we'll figure out what C is. So C is equal to A, 3i, plus 1j. And that's minus B, so that's minus 5j minus 1k, or plus 1k, because we're flipping the sign. So C is equal to minus 2i plus 2j. So then D is equal to, so we want to get D to C, so that means we're doing C subtract D. So that equals to minus 2i plus 2j, and then we subtract everything in D. So this is all quite simple. It's just very basic addition, subtraction, etc. Okay, so that's our answer. Now we could put that in other forms, but I think we'll do a question like that soon. For vector A and B, the dot product is A dot B is equal to the magnitude of A times the magnitude of B multiplied by a cos of the angle between those two vectors. So the dot product is something we use to interpret basically the relationship between two vectors. Sometimes we can use it to prove that the direction of these two vectors are perpendicular. And the reason we can do that is because it gets multiplied by a cos of the angle. And if the angle is 90 degrees, then the cos of the angle is 0. So it comes out that they're perpendicular. Now you might think, oh, so we need the angle to prove that they're perpendicular, but if we already have the angle, we know that it's 90 degrees. But not necessarily, because there's multiple ways to find out the dot product. So sometimes there's ways to find out the dot product without actually having the angle. And that's what we're going to look at sort of soon when we work with the dot product in multiple different ways. So this makes vectors used very often in geometric proofs when you have to prove things are perpendicular. That's because it's very useful to use the dot product here. So let's look at finding how here it is found the dot product between these two vectors. So what is the dot product of A dot B? Now we're going to do this in polar form because this helps us because we want the magnitude of each and then the angle between them. So that means we need their polar form. We have their polar form here that's been figured out. That's based on A is sort of like this, where there's 3 and then 1. So then, the magnitude's up here and the angle's up here. So that finds this value here. And then B is equal to sort of like this. We go 1 down and 5 across. So then our angle we can interpret, we can do it as negative, or we could also do an angle all the way around this way until we get to here. So then we find our magnitude, whatever. We have the polar form, we've been through how to get it, we just use trigonometry. Now that we have it, we can actually apply it. We can do 3.65, so that's a magnitude times a magnitude, and then times the difference in angle. So the difference in angle would be, if you get the difference between 11.31 and 18.435, that would be 18.435 minus 11.31, which is equal to some value that I'm not going to immediately come up with, somewhere around 30. And then when you plug all this into the calculator, as you will often be doing with the dot product, you will come at the result that it is 14. So that's the process of doing this, of finding the dot product if you're using polar form, but there's a much easier way to do it that I think is a lot more useful. So what we can do, instead of actually knowing what the angle is, we can use component form to find out what the dot product is, and then we can sort of understand what the angle would have been. Basically, like if it's perpendicular, the result is 0. We can understand what the angle would have been without actually finding the angle. Or like understand if the angle is something special, basically. Is it perpendicular without actually finding the angle itself? So if I want to get the dot product of A and B, what I can do is I can just multiply each of their components and then add the sum of all that together. So here we have A is equal to, let's say A is equal to 1i plus 2j, and B is equal to 4i plus 3j. Then the dot product of A and B we can very quickly find by we just do 1 times 4. That's multiplying these elements. And then 2 times 3. That's multiplying those elements. So our result is 10. So if we ever do this and we get a result of 0, that means we know the angle must be 90 degrees. Because the result must have, because the other form, if we went in polar form, we would have found that the angle between them was 0. Or was 90, sorry, 90 degrees. Now, what is the vector dot product of A dot B? Let's actually do these questions. Oh, there's already an answer here. So we have 3 times 5, 1 times minus 1, and then you find that the result is 15 minus 1 equals 14. So that's sort of the same as what we did up here. It's the same actual set of vectors, and it comes up with the same solution. So understanding that you can do the dot product this way will help you with some proofs, and it will help you simplifying your working instead of having to convert to polar form every time, which takes a lot of time. So let's find the dot product of C and D, and it really saves time when you're having to work in 3D space. So the dot product between C and D equals 10 times 2, that's this group here, minus 3 times 12, plus 3 times 4. 20 minus 36 plus 12. 20 minus 24 equals minus 4. And that's our dot product. So let's use vectors to look at proofs. Geometric proofs that you don't have to use vectors for all types of geometric proofs. It's just one way of interpreting them, and specifically given things like the dot product, some properties of vectors, it can be very useful to use geometric proofs. So we want to prove that the diagonals of a rhombus are perpendicular. Now that means we should look at a rhombus and note a few things. Okay, so we have this rhombus here. D, A, B, C. Now we should note that the opposite sides of a rhombus are parallel, and that every side of a rhombus does have the same length. So that means any vector we can make, like if we did the vector A to D, it will have the same magnitude as if we did A to B, because every straight side has the same length. So what we want to prove is that the diagonals of a rhombus are perpendicular, which is a good place to use vectors because we can use the dot product. So we want to prove that these two diagonals have a 90 degrees in there, basically. So we're going to go to a blank page. We're going to do D, A, B, C, of course. We should plot everything. Okay, so now we can start working with these values. This here gives me a little hint to work with AC and BD. I'm not going to put them in terms of B and D because I think it might confuse things a little bit, it might be better if we just work with the basic descriptions of sides. So we want to prove that this here, and let's make this a vector, this line is perpendicular to this line. They travel in perpendicular directions. We want to show that it's 90 degrees there. So let's actually put these two vectors in terms where we can actually relate them to each other. So if we want to do A to C, let's first just put it in the terms of AB plus B to C. So we're saying we go along this side and then along that side, and that's where the vector ends up. We can add them together, and that creates the vector A to C. Now we want to look at B to D. So we can put B to D in terms of B to A, and then plus A to D equals B to D. So that's going along this way and then down that way, and that finds our final vector there. So now that we're here, we can start relating, making these two look more similar to each other so that we can work with them, cancel things out and such. So let's look, okay, A to B and B to C, let's keep that. Now, B to A is actually the same as negative A to B. So we can say this actually equals the same as negative A to B. Plus, A to D is the same as B to C. So A to D, because it's the same magnitude and it's parallel, so it's the same direction. So we can put this in terms of B to C. This should be B to D. We can put this in terms of B to C. Now, where we are now, we have these two quite, seemingly related terms here, because we have B to D equals B to C minus A to B. We have A to C equals B to C plus A to B. So we can immediately see where there's probably sort of getting somewhere in terms of relating these using the dot product to find something. So now that we have these two lines, let's dot product them together. So we do B to C minus A to B dot B to C plus A to B. Now we can sort of expand this in the same way we would multiplication. So we will say, we'll expand everything into B to C dot B to C, and then positive B to C dot A to B, negative A to B dot B to C, negative A to B dot A to B. Now, we should note that multiplication of the dot product is commutative. That means that these two are actually the same, or these two are the opposite, sorry. So this is the same as that. That means we can cancel these two out because this is subtracted by that. So we end up with B to C dot B to C minus A to B dot A to B. Now, when we do the dot product, we know that we end up with a magnitude. Now, the angle between A to B and A to B will, since these are actually opposites, it's minus A to B and A to B, we know that the angle between them will be like cos 180, which is 1, or negative 1. So, since we have a negative 1, multiplied by, we should probably write out the dot product. So A dot B equals A, B, cos the angle. So with this, we end up with the magnitude of AB squared, magnitude of AB squared times minus 1, because cos 180 is minus 1. They go in opposite directions, so the angle must be between them 180. And then BC dot BC is a similar thing. It's the magnitude of BC squared. This time it's times 1, because what we have is we have cos 0. The angle between these two same vectors is 0. Here, now we realize, we go back to what we learnt before, and we realize the magnitude of each of these lines is actually the same. So we know the magnitude of A to B is the same as the magnitude from B to C, because each side of this rhombus have the same magnitude, of the same length. Based on that, now all we're actually doing is we're just doing BC squared minus AB squared, which equals 0. So the dot product equals 0 because the magnitudes of all these sides are the same. Therefore, we've completed our proof. If the dot product is 0, then we know that the angle between these two lines must be 90 degrees. So we'll look at a more complicated sort of proof here. Prove that the diagonals of a parallelogram bisect each other. So let's think about what a parallelogram has. We know that these sides are of the same length, these opposite sides, and we know these opposite sides also are parallel. And now we want to prove that the diagonals of the parallelogram bisect each other. So what is the mathematical statement that we want to actually prove? I would say we want to prove that the position of, I should be clear actually, bisect, if you haven't covered this before, it basically means if a line is bisected, it means a line is cut into two equal pieces. So if these lines bisect each other, that means they intersect at the point in which they are both halfway in length. So we want to prove that. So the mathematical statement we want to prove is we want to show that this point of intersection is the halfway point of both of these lines, is the halfway point of A to C, and is the halfway point of B to D. So we're going to quickly draw our shape again. Trying to prove that in the middle they're halfway. So we're going to pick an origin for a question like this. Unlike this question over here, where we're concentrating on, we're trying to prove something about the direction. Now we need to prove something about a position. We want to prove that the position in which they are both halfway matches. It's the same position, therefore they collide, they overlap, they intersect at that halfway point and chop each other in half. So based on that, let's look here. Let's use A as an origin position, a position which we consider everything relative to. So that means A to D, we're going to consider as just A to D. The position of halfway A to D, we're just going to put as this. Now the position of B to C, we're actually going to do A to B plus halfway B to C. The reason we're adding A to B is because since we're doing everything, we're trying to find a position relative from A, we need to move to B before we can go halfway down this line, to actually consider everything in terms of A, in terms of the position of A, to think of everything relative to the position of A. So we have, what we want to prove is we want to prove that A to B plus half B to C is the same point as half of A to D. So let's sort of follow a similar pattern that we did over here, and let's put everything in terms of these straight lines on the sides so that we can sort of maybe figure something out, cancel something, etc. I could flip We'll use C and D in this order from now on. I've sort of flipped it over. So let's put A to D in terms of A to B and A to C. So we can go A to D. Let's say half A to D equals half A to B plus A to C. And that's because we can move this amount this way and that amount that way, and then we'd end up at D. Now we can say A to B plus 1/2 B to C is equal to A to B. We're happy with that because that's already like the length of a side, and we're just trying to get everything in terms of the sides. Plus 1/2. Now, B to C is like A to C because we go down, and then it's also like negative A to B because that would move us, negative A to B moves us this way, and then A to C moves us down, so the overall line is like B to C. So we've put everything in terms of these lines, and then we can maybe start to see how we're getting somewhere. So we have 1/2 A to D equals that, and now we can figure out this. We can do 2/2 A to B plus 1/2 AC minus AB. So what this does, this allows us to move this AB into the brackets because we want to get this side, this expression to look like this expression. If they look exactly the same, if they're exactly the same, this proves that these two positions are exactly the same. So we want to move this AB into these brackets, becomes 1/2 AC minus AB plus 2AB. Put our vector lines on top, and that ends up creating A to C plus A to B. And there we have it. We've turned this here into that, because that equals this, and this equals this, and they're each the same. So we've proven that the position in which both of them are halfway, and we're looking at that relative to the origin of A, the position in which both of those vectors are 50% are halfway is the same. Therefore, they overlap, they intersect at that position and then bisect each other. So this is basically the same proof we're looking at here, but we're doing it for 3D space. So for the parallel piped below, prove that diagonals OF and CE bisect each other. So I'm going to use O as the origin this time, and we're going to follow a very similar process. So we want to do OF. So O to F, let's put OF, and we're going to go half of OF because we want to find where they bisect each other, so that's the halfway point. Halfway of O to F is equal to O to A plus O to C, or half of O to A, put all that in brackets, plus O to C plus O to D. So what that means is we went this much this way, this much this way, and that much this way, and that ends up creating a line that goes from O to F. Now, since we're using O as the origin and we want to consider C to E, we're going to first consider, we're going to make it so it's O to C plus halfway from C to E. So that means we're interpreting the position relative to O, or we go up here and then we go halfway down there, which is the same. And on this side, half OF, we're going halfway this way, and we want to find that they're the same point. So we have O to C plus half C to E. What's this equal to? This is equal to O to C plus half O to A plus O to D minus O to C. which equals to, same as last time, we can simply multiply this by 2 over 2, which makes it the same thing. And then we can give ourselves an opportunity to move this into the brackets, to move this OC into the brackets, and that will culminate in half OA plus OD plus OC. And that's the point we end up with. So then we've proven OF is equal to, half of OF is equal to OC plus half of CE. Therefore, they bisect. So with these geometric proofs, I've went over the very simple common ones that you will see around. They get much more complicated than this. It's a situation of, I think, looking at the solutions to a lot of these when you get completely stuck, and sort of memorizing them, because if you do look at the solutions and memorize them in a way, it does help you. If you memorize all the process to creating a solution, the process to proving it, then you sort of build on your tools, on all of your techniques that you know how to use to move towards one of these proofs. They can be